I'm really honored to be here. I'm also very frightened to be here because I'm a token neuroscientist in the midst of people who actually know about arts and education, which are definitely not my areas of expertise. But I did want to talk a little bit about neuroscience and creativity and to try to think about whether it can inform creativity-enhancing practices, because I think that's where the rubber meets the road. Can we get the next slide? I'm going to race through a bunch of pictures defying our instructions not to use many pictures. But as we were conversing at dinner last night, Buckminster Fuller's words came to my mind multiple times, and that is, how can we overcome what Bucky Fuller described as the de-geniusing of the children of the world? And I think that that's really what this work is all about. How can we not inhibit the creative potential of our offspring as we bring them into the world? Have the next slide. And my daughter helped me with this. I got to confess, 11-year-old twins. And so my daughter alerted me to this book, The Girl Who Could Fly. This was a girl who otherwise appeared normal at birth, but was found by her parents to start to levitate off of her changing table while they were trying diapers. And they thought this was such unusual behavior, they ended up sending her off to a special school, Institute of Normalcy, Stability, and Non-Exceptionality. Insane. And I think that this is an argument that can be made to our governing bodies that what we're doing now is insane in our educational practice, and we need to overcome that. Have the next slide. I asked my kids, I'm sorry you can't see this. My two kids are actually jumping off of a trampoline looking out over a vineyard in New Zealand, which is quite fantastic. But I asked them, what do they like about their arts curriculum at the UCLA Lab School, where we're honored to have them attend. And the one thing that they really highlighted among all other properties was freedom. That gave them the freedom to explore. In their arts curriculum, there were no right or wrong answers. And this led them to have the capacity to be more engaged because they didn't have to worry. They didn't have any fear about what would be right or wrong answers. And it also helped them forge connections among things that otherwise would have been completely disparate. They were forming connections between their guts, their feelings, the expression of their work, and the words that you describe those. Next. So there's fun studies. You can't have a neuroscientist talk to you without showing you colorful pictures of the brain, and sometimes they actually do convey information. What I think we know now is that what we do with our kids changes their brains. I mean, this should be a no-brainer, but our brain structure and function is changing constantly whenever we're exposed to novel material. That is what learning is. That is what psychotherapy is. And what we're learning, the next slide, is as we move forward, that what we can do with our brain as we learn how to use our brain systematically, we're learning how to change how our brains work. This is going to usher in the next stage of human evolution. This is not trivial. By changing the way our brains work systematically rather than by trial and error, you're going to be entering a new era, which is by definition unimaginable. Next slide. So a lot of things have changed in how we understand the brain. Oh, beautiful picture of hippocampus. Anyhow, it has lovely fibers and colors, and it is artistically elegant. But what we now know is that new neurons are born. It used to be thought just a decade or two ago that we didn't have any new neurons after about age 10. Now they can grow. And the connectivity of our brain is so dependent on activity, on what we're learning, that we can remodel the brain, and the degree of remodeling capacity is now known to be much greater than ever. Next slide. The caveat of all of this is that you probably have heard of all these neurostar disciplines. There's, in addition to the traditional disciplines of neurology, neuropsychology, et cetera, we now have neuroeconomics, neurophilosophy, even neuroart, neuromusic. And I think that the big challenge for neuroscientists is to present to you information that may be actionable, where the brain actually makes a difference. Not just putting neuro in front of something to help to explain it, but to actually take knowledge about how we can alter the brain and use that to change practices. I think that's the huge challenge. And I have no pretense of telling you that I can show you how to do that, but the hope is that by talking about some of the issues that are involved, it may stimulate you all, the experts in these, to think about how you might be able to apply some of those and principles. Next slide. So we were put this challenge by Michael Tennenbaum and his family about 8 years ago. He worked together with our chairman of the Seminole Institute, Wybrow, to found a Center for the Biology of Creativity. They invited a bunch of us neuroscientists, most of whom know nothing about creativity, to go to this horrible, harsh environment the Hotel Bel Air, in the midst of noisy swans, trying to figure out what is creativity. So next slide. We ended up with some definitions of creativity, which is often defined as manifesting both novelty with respect to the domain, what the products must be is something new, but then they also must have some value, utility, or usefulness with the domain. And this is somewhat controversial. I think Dr. Runco will give us some other definitions to complement this one later. But in brain terms, this really triggered a lot of thoughts in our minds because we can define the brain in terms of stable or flexible. There's this axis of stability to flexibility. And in my view, this resonated with what Stuart Kaufman had talked about. Activity exists at the edge of chaos. There's a stable regime and then a chaotic regime. And as you push towards the edge of the stable regime into chaos, it's right at that boundary condition that creativity is found. You can't go too far over the edge into chaos or all is lost and the thing won't be used. But if you can hold it together and bring back those novel products so they're applicable to the real world, then you have creativity. Next slide. This has been replicated, this kind of a duality, this tension between stability on the one hand and flexibility on the other. I love Yeats' vision, where they talk about gyres, the complementary forces there, the yin-yang symbol, older, and you can barely see the Tibetan eternal knot, showing this idea of fundamental complementarian balance back for thousands of years. And I think that it is this that is probably the most important aspect of practice that leads to enhanced creativity, this balance between stability and flexibility. Flexible enough to get to the new stuff and able to stabilize it, concretize it. Next slide. So we tried to figure out, well, how can we study this? We were a bunch of dull scientists. So after defining creativity, we tried to find what were the neuroscientific targets that were actually tractionable using the kind of scientific methods that we use. And we identified from the literature a series of 4 different component processes. And I'm going to race through these ultra quick just to give you a flavor of the kinds of things that we've been able to study and what are some of the things we've been able to. Only one data slide, and no one will be able to tell what that is now. So try not to have everybody go to sleep since it's only 9 in the morning. Next slide. So generation is one of the first things that we thought we could study. The best predictor of creative production, the total amount of production, even though there are occasional, creative geniuses who only produce a few works. I mean, the model is probably more like Picasso, 10,000 to 50,000 new works. Next slide, please. This is just an example. There's 199 on the left. Can everybody pick out the one that's not the Picasso? Anyhow, I couldn't. I clicked about 50 times, and I was wrong every time. But, here's an example of prolificness. Next slide. This capacity to generate new products is something that we've been able to study in other species, including the songbird. So here you see a couple of zebra finches. Everybody recognizes the male, the better-looking one. The pretty one. Thank you. The male zebra finches have to learn how to sing, attract mates when they go through adolescence. At this time in adolescence, their brain is blossoming, a particular region of the brain. We've been able to identify the brain circuits that are turned on when the boy birds begin to sing their novel songs. The degree of novelty of their songs makes them more attractive to the females up to a point. If the song is too weird, the girls stay away, right? But I think it's remarkable. Stephanie White and her laboratory have been able to delve in and determine exactly which genes are turned on, which are turned off, how it shifts the circuits in the brain that enables these boy birds to produce songs and attract mates. Next slide. Then inhibition is another critical component we've been studying. A lot of people, when I talk about inhibition, think, you have to be disinhibited, creative. But we think that's partially true, but what we've been studying is the ability to inhibit habits, because we think that's even more important in creative production. Because the first thing that comes to mind is usually not the most creative thing. The capacity to generate a product, evaluate it, and then go on to the next thing. To dig deeper and to reach higher for the higher hanging fruit in the cognitive tree. This is a trait that we think is critically important. Next slide. And, you know what, let's just skip over this. Beautiful slide, but it shows some flexible thinking of a dry retriever, a dog who doesn't want to jump in the pool, runs around the pool, and then jumps onto a mattress and then paddles his way over to the ball in order to get to the ball. Anyhow, you can see it on YouTube. This is the data slide, if anybody can recognize. Everybody, of course, recognizes this genome-wide association study. But what this... Yes, this uses recombinant inbred mouse strains. Now do I seem like a real scientist using big words like that? Anyhow, it shows that we found a genetic locus that uniquely is associated with the ability to reverse learned behavior in a mouse. And this has enabled us to figure out exactly which genes turn on a particular switch, a deep part of the brain that enables these animals to reverse from doing a habit to doing a new thing. Next slide. Then working memory. This is the easy one to explain. To generate novel ideas, I think most people recognize we need to maintain multiple ideas in mind long enough, stably enough, that we can manipulate them, making new connections and new concepts. Science of this is unbelievable. Okay, the next slide. I think I put in a picture of. This is a neuronal network grown in a petri dish. It shows that we know enough about how cells grow, how they establish connections, how they form new synapses, that we can control them, exquisite chemical precision. And these techniques, next slide, have enabled some experimenters like Alcino Silva working in our group, train mice by genetically engineering them to be smarter and have better working memory than other mice. So this mice plays three-card Monte, puts a ball underneath that cup, moves it around, and tricks. No, he doesn't really do that. It's just that's better. I got you for a second, right? He really is smarter than other mice. And this is all done just through genetic engineering, by manipulating chromosomes in the lab and then inserting them. Next slide. Then what's really one of the most important things, one of the hardest to study is how drive and emotion are fundamental to everything that we do and provide the impetus. And I think this is one of the most important messages that goes back to what my kids were saying about freedom. If we can't inspire our children, maintain their curiosity, maintain their drive, those are, I think, the cornerstones of being able to keep them going, give them the persistence to succeed and continue despite frustration. Another thing is that these same systems that are engaged in the brain in drive and motivation are also linked to our guts. And I think that one important aspect of creativity is the links of our cognitive brain to our visceral and somatic brain so that we can connect cognitive, its narratives and so on with emotions and in ways that are next slide. So some people may have heard of the concept of flow by Mihaly Csikszentmihalyi, and I think that this reflects the ultimate balancing of stability and flexibility. It's this ability to balance these traits that leads us to have high levels of generativity, productivity, enables us to inhibit the low-hanging fruit, the habits that we need to overcome, and enables us to connect things together in our mind. Next slide. So where's this all going? I don't know how many people are familiar with Ray Kurzweil's book on the singularity, but as we get into new technologies, partially in response, mind-blowing. So I wanted to include a couple of the mind-blowing stuff. Singularity is the point in time at which non-biological intelligence exceeds all biological intelligence. We already have available in the databases in the World Wide Web more data than there are words ever spoken by all humans in all history. So right now, everybody's carrying phones that have the intelligence of somewhere between a spider and a lizard. And by 2029, your typical laptop computer is going to have more brain power, according to Kurzweil, than any of us do. So what is that? What are the implications of that? Next slide. Some of it is they're going to be nanobots and neurodust, stuff you can put into your brain or sprinkle onto your brain. They'll be able to monitor your brain activity and alter your brain activity. So before I was talking about brain-changing technology. Well, this is where things are going. We are going to be able to manipulate our brain. Next slide. All of these things are already available. Behavioral training approaches, that's basically what we do in the classroom, but neurofeedback techniques, other kinds of techniques to directly stimulate the brain with magnetic fields or electrical stimulation. Next slide. These are commonly available devices. In the old days, you used to have big arrays of electrodes you'd have to slap on the head. Now, attractive young people of all kinds can wear devices that you can get for $100 or $2 and monitor their own brain waves. Next slide. Then electrical stimulation. Back at the time of Scribonius Largus, the physician of the Roman Emperor Claudius, used this torpedo fish, an electric fish, and slapped it onto the forehead in order to deliver a current and relieve headaches. And it was subsequently used for epilepsy. this kind of electrical stimulation, next slide, now available commercially for $245 if you buy now. You can also, if you go online, download instructions of how to make this transcranial direct current stimulator out of common household supplies, a 9-volt battery, a little bit of baling wire. So this is available now. What are we going to do with this stuff? Next slide. Well, I think here's where we need to think about both the benefits and the risks. This is a map of the London city streets. One of the cornerstones of the neuroplasticity revolution has been the study that London taxi drivers got a bigger, fluffier hippocampus. And then it was recently confirmed in a longitudinal study as a result of their training. Next slide. You can see, you can't really see on this slide, but this is a nice picture of brains, and you can see the little red spot there is their hippocampus where it got bigger. Next slide. Amazingly, the people who studied well and learned this, they're the ones who got the bigger, fluffier hippocampus. It was associated with the time they spent training and how well they did on their exams. The amazing thing that's not much noted is that there was an adverse effect. People say, oh, what are the adverse effects of brain training? I say, oh, how bad could it be for you? Turns out the people who got this special training and got bigger hippocampus ended up being worse at other nonverbal memory procedures. So I think that the idea that there's some techniques that are all gain and no pain is probably not true. We always have to think about what we're doing, what is that going to be doing with our brains, and how is that going to be changing what we know. Next slide. At UCLA, we've been trying to leverage some of these ideas and do healthy campus initiatives. I have the honor of being in charge of the Mind Well program. We also have things for eating, moving, and the built environment, which is particularly amazing to be here in Gehry Studios to think about how the built environment interacts with well-being. So maybe talk to me about that. But we're really trying to pull together events on the campus to try to promote well-being in all of these aspects. Next slide. Part of our goal is to look at promotion of creativity and other things that we believe will support well-being at UCLA. But also, as you can see, some help with logo design. I know there's some designers around here. This is what happens when you let a neuroscientist. Next slide, please, quickly. We started teaching a summer institute in brain, mind, and wellness. I teach a course in personal brain management, another course in mindfulness practice and theory, integrative East-West medicine. But these are things that are happening now that anyone can come and join. Next slide. We also opened a brain gym so that people can come in and learn about these new technologies, learn how to modify their brain, learn how to potentially enhance creative cognition, learn what the risks and benefits may be. Next slide. We also have a new initiative that's a north-south campus integration that's trying to bring the arts to connect better with the lower campus, with our health campus. And so I'm very interested in ideas about how we can promote that. Just an example, I gave a talk up at Arts and Architecture, and they said, oh, we're going to put a brain on the poster. I said, oh, no, what's going to happen when the artists get on brains? And they got the most beautiful brain I've ever seen. Really nice. So I wanted to congratulate artists on having a better appreciation of brain art than most of the neuroscience. Next slide. And then the ultimate goal of this broad campus effort is to try to deal with the 90% of people that are usually not attended to. Biomedical science focuses on the sickest 10% of people. But we think the dialogue needs to be moved, and this is where the educational initiatives really take hold. We need to worry about the entire population and lift all boats by a noticeable amount on fundamental dimensions like stress resilience or creativity. And it eliminates a lot of health problems, and it provides a new foundation for the future that couldn't be realized in other ways. Next slide. And we started a new project. God bless the John Templeton Foundation have funded us to move beyond some of the studies that we've been doing on what we call little C or everyday creativity, trying to understand what are the cognitive contributions to that. And now we're starting a new big C study where we're studying world-renowned visual artists and scientists and trying to understand whether they're really outliers. And so I was so excited when I heard Frank Gehry mention last night he wants to be used and abused. So I'm declaring now in front of all of you who may have heard that we would like to use and abuse him and study his brain quickly so that we can include it with our other. So anyhow, with that, I'd also appreciate other ideas of other creative geniuses who you think we can study their brains for the benefit of everyone. Next slide. With that, I'll thank you very much for your attention and almost stay with it.
You did great.
Say, Robert.
Thank you very much.
Do you have a fish you could slap on my head?